This recording is for M31 curve sketching. Some of the material that we go over is material that you are familiar with from previous math courses. And then some of the material has to do with some stuff we've learned back in previous modules, and then some material is new. And we really are looking at taking all these ideas, which I'll flush out here in a moment, and figuring out how we could sketch a very detailed curve without the use of a calculator. Okay, this is kind of pre-calculator stuff. All right, so we're going to do a little overview of the entire module, and I'm going to flush out one question in detail. The first section, I don't have a lot to say about, because we've been working with domain and range since way back in grade 10. So hopefully you are pretty adept at stating domain and range. The one thing that I could say is to know how to note it in set notation, and then making sure that you also know how to note it in interval notation. And look through, nice spelling there, sorry. I did look through the book a bit, and it seems to me that they like interval notation mostly, but I don't want to stand on that. So there'll be one of two ways of writing domain and range. So be aware that you will likely have to write some domain and range. Now, in with that, so in section 2, we talk about asymptotes, which actually helps us to flesh out what the domain and the range is. So let's talk about some asymptotes. And again, you have done some work on asymptotes before this. So some of this will be familiar, some of it may not be. So there are 3 types of asymptotes. And this has a bit of a calculus bent. When we're looking for a horizontal asymptote, we're looking for the limit as x approaches infinity. Okay, so all of those rules that we did way back, I think it was in module 2, where we were learning about limits as x approaches infinity, those skills are going to be brought back in here. I don't think it's a time to go back and do lots of that. You can go back and watch some recordings, but that's how we find a horizontal asymptote. A vertical asymptote is found by looking for where x is equal to 0 in the denominator. Okay, so these will come up when we have a rational expression with x's in the bottom, and then we're looking really for non-permissible values is what we're looking at when we're talking about vertical asymptotes. Again, that's something that we did back in 20-1 and 30-1, and so something that in this point in the recording I'm not going to flesh out too much. What is new is how we find oblique asymptotes. Okay, so what we have to do oblique asymptotes, you remember back doing polynomials, and you may remember you had to do long division of polynomials. And then your teacher probably said, well, long division is kind of a pain in the neck. Let's do synthetic division. And you might have forgotten about long division. Well, long division helps us to find oblique asymptotes. So what we do if we had a question, say we had something that looked like this, x cubed over x squared minus 1, then we would set it up as long division. And we would divide, and whatever we got for the quotient, now I don't know if you remember all your terminology, but this guy up here is the quotient, is what the answer for the oblique asymptote would be. Division, you divide the first term of the divisor into the first term of the dividend. So step 1 would be x cubed divided by x squared, which would give you x. And you would put the x up here. Then you multiply through the entire denominator. So you may remember that you might have to put some 0 terms to decrease 1 by 1. Whoops, this should be x cubed minus x squared. This subtracts to 0, and this subtracts to a positive x squared. 0 take away a negative 0 take away a negative 1. So what I'm trying to spit out is x squared. And so then we do it again. So step number 2 in terms of the division is to take the beginning part of the dividend, divide by the beginning part of the divisor, and get 1. Put plus 1 up here, and then multiply the plus 1 through the entire divisor. Again, I'm going to have to put another placeholder for 0x. So we get x times 1 times x squared, sorry, is, I'll carry this down here so we know where we are. So we get x squared minus 1. Now, what have we got here? Oh, yeah, so I see. So I did, yeah, again, I just did an example. It's not the greatest example here because I've missed a term. Let's throw this x in here so things work out. So we're dividing by, so that things are decreasing by 1. I guess that's the price I pay for just, boom, throwing a question up here. So our division to that point is okay. Let's just on the side, in case I've lost anyone here doing this, we're going to go and we're going to multiply the whole entire divisor by the 1. Okay, so we're putting the answer down here. So we get x squared minus 1x. We subtract and we get x remainder. Now, once this term falls below the degree of the divisor, we're done. And so we would write our answer here. The quotient is our actual answer for our oblique asymptote, because what we would get if we're trying to break this up, again, if you've done math 30-1 fairly recently, this might ring a bell for you, as we get x plus 1 plus the remainder of x over x squared minus 1x. So this piece is the oblique asymptote. Y equals x plus 1. So sorry about that. I should have had an x in the divisor there. So there's a little bit of math that goes on trying to find oblique asymptotes for sure. Okay. Now, section 3, I'm kind of breeze over section 3, but I am going to cycle back to it. It has to do with the use of first derivatives and how we use first derivatives. Now, first derivatives help us to find what are called stationary points. And then they help us to figure out whether they are maximum and minimum points. But what I would like to do is just sort of just put that on hold for a minute, because I'm going to go to section 4 and talk about second derivatives. And then I'm going to do a question that involves, that comes and cycles back to first derivatives. So I'm just going to leave that kind of there. Okay, so section 4. We haven't done a lot of work on second derivatives to this point in time, a little bit. So of course, the second derivative is you have a function, you take the first derivative, then you take the derivative of the derivative. And that's where you come up with the second derivative. Now, we use the second derivative to help us to figure out whether we have, whether the stationary points are maximum and minimum, and whether they're concave up, concave down, etc. So I'm going to kind of jump aside from just doing second derivatives, and I'm going to go, the question that I'm going to choose to do is in your little booklet, but I'm going to do it 3 different ways. Okay, so if you want to refer to your booklet, I'm going to do page 89. Example 3, and it's going to help flush out first derivative work and second derivative work, hopefully kind of all in one example. So the example says, you don't have to go get your booklet out. I'm trying to change in the example a little bit. 3 different tests to determine the maximum and minimum points of, and the equation is f of x equals 1/3 x squared x cubed minus 1/2 x squared minus 6x plus 1. Okay, so here's what we need to do. Step number 1, we have to find what are called the stationary points. Now, stationary points, let's think about what stationary points are. When we talk about stationary points, what we're talking about are we looking for points where the slope is 0? Okay, so think about what that means. Graphically, we're looking for a point that looks like this, where our tangent slope is 0, or we're looking for something like this, where our tangent again is 0. Therefore, to figure this out, we're looking for where the first derivative is equal to 0. That's how we identify where we're at least going to start looking on our graph for where a stationary point would be. Okay, so step number 1 is we're going to have to do some derivative work. We're going to have to figure out where they are. Then we're going to look at the 3 different ways to figure out whether they're maximum or minimum. So let's blast off. Find the first derivative. We're going to have 1/3 times 3x squared meant okay, so I'm not quite out there. Let's go back at this and see if we can finish up. Not quite sure what happened there. So we're looking for when the first derivative is equal to 0. So now you can see we have a nice little factoring question. So we're going to go and factor it. This is nice and straightforward math. We're trying to find something that has a product of -6, a sum of -1. So we get our factoring to be x minus 3 and x plus 2. Therefore, our 2 x coordinates of our stationary points are x is equal to 3 and x is equal to -2. Now, when we're actually asked to find stationary points, we need to find coordinates for the points, okay? So we need to take and go back, and you have to be really cautious whether you're going into f at x, the function, f prime of x, the derivative, or f double prime of x, which is the second derivative. You have to be really clear as you're going through these. So we are going to go back, and I'm just going to write down the original function here so you have it right in front of you. And we're going to substitute 3 in and find the y value for that. And so just you can just do the math. You can, this is fine to do in your calculator. It turns out to be -25/2. I'm not going to worry about doing the math there. That's kind of not the point. And then we're going to put f at -2 in. So 1/3 -2 cubed minus 1/2 -2 squared -6 times -2 plus 1. Yeah, throw it in, you jimmy it around, you shake up your calculator, and I think the answer comes out to be 25/3. Okay, so we have our 2 points. One point is 3 comma minus 25/2, and the second point is -2 and 25/3, like that. Okay, so these are our stationary points. So at this point in time, all we know is that the slope is equal to 0, or f prime of x is equal to 0. We don't know whether they're maximum, or we don't know if they're minimums. So now I'm going to show you 3 different ways to test to see whether they're maximum or minimums. I don't like the first way. To me, the first way really is not a lot of mathematics in the calculus stream, but it's something that I need to talk about. And the second 2 ways I think are very valid. Okay, so what do I have? How am I numbering this? Okay, so this is step 2. So step 2, 3 tests to determine max or min. The first kind of test is to look at your x value, 3, pick an x value to the left, find out what the value of the function is, pick an x value to the right, find what the value is there, and then decide whether they're lower or higher than your y value. So what we've got here, if we look at this kind of, on a grid, over at 3, we're down at minus 25 over 2. And I don't really care, again, how perfect it is, but it's down here. Okay, so at 3, and I'm going to put minus 12.5, just so we have a little visual on that. And then our other point is over here at minus 2, and it's up here. Now, we can maybe suspect just by graphing that minus 2 is going to be a maximum, and the positive 3 one is going to be a minimum. So you can do some of the just the graphing to make sure it's okay. But what we're going to do is we're going to pick x value over here and an x value over here, and we're going to find the y values. So a little bit before minus 2, heck, you can pick minus 3, make your life a little bit easy. So when we test for this point, we'll do it one at a time. We're going to pick, say, minus 3, x equals minus 3, and figure out the y value. And then we're going to pick one on the other side. Let's pick x equals minus 1, and we're going to find the y value. So you have to throw that into your f at x and work it through. Again, since it keeps on, I'm scrolling down, I'll put the f at x function here. It's 1/3 x cubed minus 1/2 x squared minus 6 x plus 1. Okay, so I'm just going to grab my calculator. I'm not going to stand on ceremony. I'm going to figure out what these numbers turn out to be. Okay. So you can see these questions so far, I don't think they've been incredibly hard, but they are long. So be aware that they do take a while. Hopefully I don't make any mistakes in my calculator work here. And then plus 1, let's have a look. 1/3 minus 3 cubed minus 0.5 minus 3 squared. Okay, so we get 5.5. Now again, if this is easier over here on the left-hand side, that's minus 2 and 8 1/3. Okay, so again, this is below, so it's about here. And then let's do x equals minus 1. I suspect we're going to get 5.5 because I think we're going to have some symmetry. But anyway, let's just do it. 1 divided by 3 times 1 minus 0.5. Well, this is much easier. Minus 6 plus 1. Okay, so we get, I think I messed that up. 1 divided by 3 times, minus 1. That's my problem. And then take away 0.5 times minus 1. Plus 1. See, I don't get it to be symmetrical. Now, maybe my numbers are out. I'm not quite sure. But again, it's below. Okay, so we see that by picking a number to the left and a number to the right, we can see that this is going to prove that this is a maximum. And then the next one you would do is you would go to 3, and well, it's about minus 12.5, and you would figure out what the value was when x was 2, perhaps, or you don't even have to go to another new even number, but I kind of like that. Find out what x is equal to 4, and then find your y values. I'll leave that with you to do. So we've figured out that this is a maximum because these are lower, and when you do this, you'll figure out that this is a minimum because they're going to be higher. They're going to be up in here somewhere. Okay. So that test to me really doesn't apply very much derivative work. Okay, so I want to talk about the other two tests that we have. Test number 2 is to find the value of the first derivative on either side, and then make some, decide what's going on based on the first derivative. So remember, if again, I can just scroll back, that the first derivative expression was x squared minus x minus 6. So x squared minus x minus 6. So we're going to find out again what's happening on either side of both of these points. This is one of our points. This is our stationary point. This is our other stationary point. So we still do the same thing where we pick an x coordinate to the left and an x coordinate to right. We might as well pick the same ones. We put them in here and we evaluate. So when we're going to look at this point is what we're going to look at first. Again, we're going to go left to right. So we're going to figure out what's happening at x equals minus 3. Okay, so the first derivative is minus 3 squared minus minus 3 minus 6. This one I think I can do in my by myself. So we get 9 plus 3 minus 6. And that works out to plus 6. So that's a positive. Just keep in mind that's the key. The 6 is not that key. It's whether it's a positive or a negative. And now we're going to look at what happens at x equals minus 1 on the other side of that point. Okay, so we're going to find the first derivative. And so we go minus 1 squared, take away a minus 1, take away a 6. That turns out to be 1 plus 1 minus 6. Again, we're only worried whether it's positive or negative. It turns out to be negative 4. So think about what that means. First derivative is slope. So this means that on the left-hand side, we have a positive slope. And maybe what I'll do is I'll change my colors. So right here, we have a positive slope. And then on the right-hand side, we have a negative slope. When we have the slope, which please read it as f prime of x, go from positive to negative, we have a maximum point. Okay, so it goes from positive to negative. Visually look at it, it's going up and then it comes back down. That's the test that would tell us that for sure this is a maximum point. And then again, repeat that idea for the next point. So 3 and minus 12.5, I have it that way. I might as well just leave it that way. And so we can test before and after. I didn't, fill that all in, but we're going to test x equals 2 and we'll test x equals 4. So in this case, we better have it going from negative to positive, right? To show that we have a minimum. Let's just, confirm that. So f prime of x is 2 squared minus 2 minus 6. So that's 4 minus 2 minus 6. Again, we're really only worried whether it's positive or negative. So that's minus 4, which is negative. Again, if we do some color coding, that means it's going down like that. Put x is equal to 4 into the first derivative. We get 4 squared minus 4 minus 6. That is 16 minus 4 minus 6, which is positive 6. The positive is what we care about, goes this way. We go back up on here then, and we do our slopes. The slope on this side is this way, and the slope on this side is that way. That's showing us that it's a minimum point, okay? So when f prime x goes from negative to positive, have a minimum point. So this guy is a minimum point. Okay, which we decided from test number 1. We're not going to get different answers from the different tests, or we're going to get a great deal of trouble. Now, it's been a little bit of a long recording. We're in the second derivative area, and we're going to talk about the second derivative test as the third type of test. So the third type of test is taking the second derivative. Now, just for argument's sake, I think it's useful to have our points back here. So mine's 2, and what was the 25 thirds is the one point we're looking at, and the other one was here. It was 3, and whoops, I love doing that. It's so funny. Bracket 3 and minus 25 over 2. Okay, so you got to do the second derivative. So here's the first derivative expression. X squared x minus 6. Let's take the second derivative. We get 2x minus 1. Same thing. We're going to take a point, an x value on the left and an x value on the right, and see what we have going on. Okay, so there is some similarities here on these tests. So we're going to go to x is equal to, I think it was minus 3 was what I had chosen. So the second derivative is 2 times minus 3 minus 1. Again, we're really just concerned with positive, negative, but we get negative 7, which is a negative. And then we're going to go to x equals minus 1. And what does that work out to be? It works out to be minus 3. So we get another negative here. Now, I got to back up a little bit. Sorry about that. When we're doing the second derivative test, we don't have to do either side. I'll leave it there, but we don't actually have to do either side. We throw the x value of the point in. So I have to back up a little bit. I don't want to redo the recording, so I'll just kind of re-explain this. So we've got our second derivative here. And we've got our point. This is one of the points we're checking. We're just going to put the x value in there and see what happens. So we get f double prime of x is 2 times minus 2 minus 1, which turns out to be minus 5. We just didn't have to do this part. Okay, so that turns out to be negative. All right, so negative, again, it's more important than it's negative. The 5 is not so important. So the second derivative, when we say negative, is less than 0. When we have it less than 0, when the second derivative is less than 0, it means that our graph is concave down. This is something you will need to know. Concave down means opening down, which means maximum, right? So when the second derivative is negative, we have a concave down or we have a maximum. Okay, so again, I'll just get rid of this. We didn't have to do on either side here. That's my bad. Too long of a recording, talking too much. Okay, now we do the other point. The second point was 3 and minus 25, 2. So the same thing. We're going to take the second derivative. We're going to put 3 in. Really just concerned with positive, negative. So 6 minus 1 is 5, which is positive. Okay, that tells us that f double prime of x, the second derivative, is greater than 0, which means it's concave upwards. Concave upwards look like this. Therefore, it's a minimum, which is what we already knew we were getting to, but that's the third test. Okay, so lots of work to try to flush out the 3 different ways. You can come back to the recording, sorry about my little blip there on the second derivative, to look at the different ways. The last thing on the second derivative section is if you're trying to find a point of inflection. Now, point of inflection, do you remember cubic functions? They went like this. They had kind of a, I didn't ever know what to call them, but they're kind of like a squiggle. That's a point of inflection, okay, where they sort of are going to be concave down and they turn to concave up. Or they're going concave up and they turn and they're going concave down. We find those by finding where the second derivative is equal to 0. Points of inflection happen when the second derivative is equal to 0. And that's all I'm going to say there. Now, I think the last thing that I want to do here is just talk a little bit about symmetry. Okay, so a test that we'll be asked to do is try to figure out whether the graph is symmetrical about the x-axis or symmetrical about the y-axis. So the tests for that, again, not super hard, but if we're asked if it's symmetrical about the x-axis, what we do is we if the expression or the equation, equation stays the same, it is symmetrical. About the x-axis. So you just replace y with minus y, and then you reduce and do your math, make sure you get the same statement or you don't. And then possibly by course of suggestion, shall we say, that being symmetrical about the y-axis is just kind of the reverse, right? We replace the x with minus x, and then we do the same thing. If the equation basically, I don't know if I should say stays the same, but reduces to the same thing, So I'm going to just say it stays the same. It is symmetrical about the y-axis. So that's another little piece of the puzzle in terms of trying to figure out how to do a long-handed question. One other thing just to note before I finish up, and again, not a lot to say about this, is intercepts. We know how to find intercepts. So you'll be asked to find the x-intercepts by obviously setting y equal to 0 and solving. And you might be asked to find the y-intercepts by setting x is equal to 0 and solving. Okay, so that's something that goes way back to grade 10. Okay, so I'm going to wrap it up. I hope to do another recording on Module 5 with another question, maybe slightly more difficult than what I did in this one.